So far, we've looked at linear functions, quadratic functions, and higher order polynomial functions as various ways that we might model situations in the real world. We're going to try one more kind of function before we move on from this general topic, and that is the rational function. You might recall that rational has as a part of its name the word ratio. And that's because a rational function is a ratio of two polynomial functions. So we could say f of x is equal to p of x over q of x. But we have to, since q of x is in the denominator, we have to stipulate that q of x cannot equal 0. So this is a function that often has some areas that are undefined, because anytime q of x is 0, the function's undefined. We're going to start looking at something called a linear rational function. And it's called that because both p of x and q of x are linear functions. So let's look at f of x is equal to 2 over 1 plus x. Okay, and this obviously is a linear function, and this is a constant, but we still consider this a linear rational function. And we're going to make a graph of this by creating a table. So I'm going to have x in the first row of my table, and then x plus 1 in the second row, and then I'll have that f of x equals 2 over x plus 1 in my third row. So we'll start off with, I'm going to use some numbers that are a little bit closer together than I usually do. Okay, now when I add 1 to each of these, I get negative 0.5, negative 0.2. And now when I put these in this function, all of these numbers are absolute value less than 1, so pretty small, which means that my third row is going to get a little bit larger. So if I were to graph this, put y-axis right down the middle, x-axis here. No, we don't want x-axis down there. Put x-axis in the middle as well. See, my values of y go from negative 200 is the largest one, which is not going to go on my graph. 20 and negative 20 probably are the easiest ones to put on the graph, so we'll go negative 5, 10, 15, 20. And my values of x are between negative 1.5 and negative 0.9. So, negative 0.5, negative 1. So at x equals negative 1.5, I'm at negative 4, so about there. Negative 1.2, I'm at negative 10. So that would be here. Negative 0.1, I'll be at negative 20. So it's negative 1.1. And then, of course, at negative 1.01, I'm at negative 200, which is going to be way off of my scale. I can see that there's a symmetry here. So at negative 0.9, I'm going to go up to positive 20. So this was 5, 10, 15, and 20. Negative 0.9 would be there. And then going on from that, opposite this would be negative 0.8, would give me the value of 10. And then if I'd gone on to negative 0.5, I would have had a value of 4. This is not a lot to go on, but I know that the general shape of a rational function looks like this. And up here it would come down and curve this way. So this is the general shape of my function. And you might have noticed that this curve comes over here and gets very close to negative 1. Never actually gets there. I went to negative 1.01, so just to the left of that. And then I skipped over to just to the right of it, and that's where I got my positive and negative 200. So this is generally the shape of the graph. And the graph's not defined on this line of x equals negative 1, because at x equals negative 1, this would be 0. Okay, so this is generally what the graph looks like. And at a point where a number makes the denominator 0, but it doesn't make the numerator 0, we call that a vertical asymptote. So this graph has a vertical asymptote at x equals negative 1. The function is not defined there. So I've got a function that's in two parts with a break here at negative 1. Pause the video now and work on checkpoint 1. In our last example, we looked pretty closely at the area where the graph was undefined and call that the vertical asymptote. But rational functions often also have a horizontal asymptote. And a horizontal asymptote is also a line, horizontal of course, where the function is not defined. Let's look at how we find a horizontal asymptote. We're going to graph this function. And we'll look first for the vertical asymptote, which would be if 2x plus 4 equals 0, that means that 2x equals negative 4, and x would equal negative 2. So that's going to be our vertical asymptote. And we always find the vertical asymptote by setting the denominator equal to 0. Now we want to think about what happens to this graph when x gets very, very large or x gets very, very small. So let's look at large first. Let's say x is 1,000,000. If x is 1,000,000, then the numerator would be 3,000,000 plus 2. The denominator would be 2,000,000 plus 4. At that point, the plus 2 and the plus 4 really don't matter. Okay, 3,000,002 divided by 2,000,004 is essentially the same as 3,000,000 divided by 2,000,000. Okay, and we call this result then, if it's 3,000,000 divided by 2,000,000, it would be 3 over 2. And we call this the horizontal asymptote. Okay, and the same thing would happen if I let x be negative 1,000,000. The two negatives would cancel out and we'd still end up at 3 over 2. So if I wanted to graph this function, I know that I've got a vertical asymptote at x equals negative 2. So I'm going to sketch that in here. My horizontal asymptote is at 3 over 2, or more properly, y equals 3 over 2. So we'll put that one in here. So I've kind of divided my graph into 4 pieces. And my rational function is going to be contained in 2 of these pieces. You see them here, 1, 2, 3, and 4. So the trick is to find out which pieces. Okay, I could plot a couple of points that would give me an idea. What happens when x is 0? This goes away, and I'm left with 2 over 4. So at x equals 0, y-axis, my function has a value of 1/2. Okay, I could do the same thing with x equals 1. Then I would have 5 over 6. So at x equals 1, I'm up here getting pretty close to 1. It's reasonable to assume then that at x equals negative 1, I'm going to get a point down here somewhere. But let's check it out. Negative 3 plus 2 would be negative 1. And negative 2 plus 4 would be positive 2. So I would be at negative 1/2. So at x equals negative 1, I'm at negative 1/2. So I can see the beginning of the curve here, and I can just kind of sketch it in. Between the points and the asymptotes, I know pretty much what that looks like. Now, I haven't sketched anything over here. Let's pick x equals negative 3 and see where that ends up. If x equals negative 3, this is going to be negative 9 plus 2, so negative 7. And then this will be negative 6 plus 4, so negative 2. or positive 3.5. So at negative 3, we're at positive 1, 2, 3.5. Now let's look at negative 4. This is going to be 3 times negative 4 is negative 12 plus 2, so negative 10. This is going to be negative 8 plus 4. So that's going to be negative 4. And 10 over 4 is the same as 5 over 2, or 2.5. So negative 4, we're about here. And we can kind of see that this graph is starting to look like that. So that's our rational function with both a horizontal asymptote and a vertical asymptote. Pause the video now and work on checkpoint 2. Now we'll look at a rational function where both the numerator and the denominator are quadratic functions. So we have f of x is equal to 2x squared over x squared minus 4. Okay, I want to start here with factoring this so I can find the places where it's 0. X squared minus 4 is x plus 2 times x minus 2. So if x is either positive or negative 2, this is going to be 0, and the function will be undefined. So I'm going to go ahead and draw my y-axis here, and then I'll draw asymptotes, 2 units to either side of it, for those areas where the function is undefined. Okay, the number that would make the numerator 0, if 2x squared equals 0, then x has to equal 0. Okay, I can find a horizontal asymptote by dividing this, both the numerator and the denominator, by x squared. Okay, when I do that, on the top I get just 2, and on the bottom I'm going to get 1 minus 4 over x squared. Okay, using my idea once again, as x gets very, very large, this number is going to get very, very small. And so it won't even really matter. And my horizontal asymptote is going to be 2 over 1. So if I make the x-axis here, then the horizontal asymptote is right up here. So now I have 6 regions with my 3 asymptotes, and I need to plot points. And if I do that, I find that this rational function has a curve here in between these 2 vertical asymptotes that looks kind of like a downward opening parabola. And then it also has a curve up here and a curve over here. So a little bit different looking function. So pause the video now and work on checkpoint 3. I gave you some fairly specific procedures for finding the value for a vertical asymptote, but we haven't talked as much about how specifically to find a horizontal asymptote. There are actually 3 rules for horizontal asymptotes. Let's go over those now. If I have a function, let's just say f of x equals x squared, that's 2x squared plus 4 over 3x. In this case, x squared is going to get large faster than x gets large as we allow x to get very large. So this number is going to be larger and larger and larger. This number is going to be larger, but not by as much as this. So we say if the degree of the numerator is greater than the degree of the denominator, that just means this number is going to get very large, and I'm dividing it by a smaller number, so it'll get a little bit smaller, but not significantly. And we would say that there's no asymptote, or no horizontal asymptote. Let's say that. Okay, because this is going to just continue to get larger and larger and larger. How about if I did this? This is the situation we looked at a little earlier. If I have an x and an x, as x gets very large, this constant term tends to be insignificant, and so my horizontal asymptote is equal to the numerator leading coefficient, which is the coefficient of the highest power of x divided by the denominator leading coefficient. So for this function, the horizontal asymptote is equal to 2/3. So I just take these two numbers. Okay, we've got one more situation. What if the denominator degree is larger than the numerator degree? When I make x very, very large, this is going to be much larger than this. And what happens when I have a number divided by a number that's much larger? Let's think of it this way. We'll stick with this. Let's say x is 1,000,000. So I'm going to have 2,000,000 divided by 3,000,000 squared. So like that. What's going to happen? When I take a small number and divide it by a very large number, eventually it goes to 0. So if the denominator degree is higher, the horizontal asymptote is 0. Okay, so those are your rules for horizontal asymptote. And I would encourage you not to necessarily memorize those rules, but think about what happens when x gets very large. What happens to the value of my function? I think that's a little easier way actually to remember it, to reason it out, than try to memorize some rules. Let's go on now and look at an application. This particular problem's got a rather lengthy introduction, so I'll just read that to you. It says, in many situations involving environmental pollution, much of the pollutant can be removed from the air or water at a fairly reasonable cost. But the small amounts of the pollutant that remain can be very expensive to remove. Cost as a function of the percentage of pollutant removed from the environment can be calculated for various percentages of removal, with a curve fitted through the resulting data points. This curve then leads to a function that approximates the situation. Rational functions often are a good choice for these cost-benefit functions. So let's suppose that we have a cost-benefit function like this. F of x is equal to 18x over 106 minus x. X is equal to cost in thousands of dollars. Okay, we would say the domain of x, that x could be anywhere between 0 and 100 because it's, this is f of x. F of x is the cost in the thousands of dollars. X is the percentage of the pollutants that we're going to try to remove. Okay, so basically what we're saying, pretty easy to get out some of the pollutants, a fair amount, but if we decide that we've got to get out every last percent of pollutant, it's going to be expensive. So to remove 100% of the pollutant, we'd write our function as of 100. So it's going to be 18 times 100 over 106 minus 100, so 1800 divided by 6, which would give us a total of $300,000 if we're going to remove everything. So let's say, well, I don't really have $300,000. Could I get away with doing 95% of the pollutants removed? So now I'm going to have 18 times 95 over 106 minus 95. And at this level, it's only going to cost me $155,000. So just a little more than half of what it would cost to get everything. Okay, working another level. What if I was satisfied with 90%? And 18 times 90 over 106 minus 90, and this would cost me about $101,000. So you can see, depending on what level of cleanliness we need, we can lower the price to something that's going to fit within the money that's available. So pause the video now and work on checkpoint 4. Another rational function that's useful in business is called the product exchange function. For many companies, farms, or other business enterprises, the amount of one item that can be produced is affected by the amount of another item. They may share equipment or other resources, so that when the production of one item goes up, the production of another item must come down. Okay, a good example of this is when you're processing crude oil. If I process crude oil to make the maximum amount of gasoline, then I won't be able to make as much diesel fuel. So there has to be a balance there. And so let's look at a product exchange function and see how this works. So this is a function for the fruits of the earth winery for red wine X and white wine Y. So Y is equal to 150,000 minus 75x over 1200 plus x. Remember that x is cases of red wine and y is cases of white wine. Okay, I want to find the maximum quantity of each kind of wine that can be produced. So we're going to get the maximum quantity if I only produce one item, devote all my resources to one item or the other. So let's look at, let's say I want to produce all red wine. So I'm going to let this equal 0. And that means I can, if I could multiply by this denominator, this would still be 0. So if this is still 0, then I have 150,000. I can make that equal to 75x. Just move the equal sign here, and then divide by 75. So these cancel out. And I get that x equals 2,000. So if I made no white wine at all, I could make 2,000 cases of the red wine. Let's work it the other way now. What if I made no red wine? And I have y equals 150,000. This would go to 0. This would be 0, so just divided by 1,200. So I've got 1,500 divided by 12, which is going to give me 125 cases of the white wine. Okay, so this is called a product exchange function. And we have lots of these kinds of things in life besides just in business. If you think about when you're taking 2 or more courses and you have a limited amount of time, you've got to divide that time up somehow so that all your courses hopefully would have a grade of 70 or higher. You know, to get the maximum grade in one course, you might have to sacrifice another. So pause the video now and work on the last checkpoint, and then you should be ready to go on to your homework.